Hi, everyone. My name is Ivanica, and this is John. And we're CS PhD students at Stanford University. Today, we're excited to present OpenJarvis, a popular open source framework that's bringing personal AI onto your personal devices. Personal AI has become central to daily work, but almost all of it lives in the cloud. Today, we show how you can move the core of that stack, namely the inference, agents, memory, and learning, onto the device. Personal AI is everywhere now. So frameworks like OpenClaw, Hermes Agent, they handle writing, research, coding, scheduling, and run continuously. But almost every query goes to a cloud frontier model. As a result, these frameworks are expensive, not private, always online, and incredibly energy inefficient. However, this does not have to be the case, and two tailwinds are working in our favor. First, local models are finally good enough. Open-weight models like Qwen 3.5 and Gemma 4 trail frontier cloud models by 6 to 12 months in terms of capabilities. On top of that, consumer accelerators, things like the AMD Ryzen, the Apple M series, the NVIDIA DGX Spark, now run 1 to 128 billion parameter open weight models. So the bottleneck right now isn't actually the raw model capabilities. Rather, it's a system around it. So this brings us to our guiding question. Can the core of the personal AI stack, namely model inference, agent execution, memory, and learning, run entirely on device while staying competitive with cloud-only stacks? And to answer that question, we introduce OpenJarvis.
OpenJarvis is composed of two main components: the spec, which is a typed configuration object decomposing the personal AI system into 5 editable primitives, and the LLM-guided spec search, which allows a local cloud search algorithm to jointly optimize 4 editable primitives. To start off with the primitives, there are 5 main components within. There are 5 main components within the OpenJarvis architecture. The first is the intelligence, otherwise the model that's actually running. This can be a Qwen family model, a Gemma family model, or whatever open source family that you're looking to serve. The second is the actual inference runtime. So what is the actual engine that is running this model? This could be Ollama, this could be Llama CPP, this could be SGLang or VLLM. Beyond the engine itself, we also have the agent logic or the agent, which is what the actual intelligence and engine sits within. This is what's actually orchestrating the different tool calls, orchestrating the different LM calls to actually provide the experience for the user. The fourth component is the actual tools in memory. There are a lot of different things that allow an LM to actually provide utility to the user. Sometimes these are search API queries. Sometimes these are different Docker containers for running coding environments. All of these are interacted to with an MCP server that allows the agent to call what it needs when it needs it. And finally, we also allow different kinds of learning algorithms to help improve the whole system over time. This can be traditional weight improving techniques, such as SFT, supervised fine-tuning, as well as more parameter-efficient techniques, such as LoRa. This can also be simple prompt engineering techniques that allow you to compound these capabilities over time. This includes JEPA, DSPy, and other frameworks. Now, we'll step into the actual, into a video showing the actual way that we interact with OpenJarvis, whether it's the CLI or the desktop app. So if you could start this video. Nope. So there's a few different ways that you can interact with OpenJarvis. One is the classic CLI, in which you can interact with it in a terminal. The second is the desktop app, in which you can interact with it the same way you'd interact with a ChatGPT or a Claude desktop app. And this allows you to ask all different kinds of queries, regardless of domain. This can be deep research style queries in which you do research on different subjects. This could be just classic chat queries or reasoning queries for whatever domain subject you're looking for. But the important thing to note with all of this is all running on device. So rather than having to constantly be querying and constantly requiring a Cloud LM to do your daily workflows and do your daily schedule, you can instead rely on intelligence that is owned and provided on your actual device without having these constant latency costs, dollar costs for every single time you interact with the intelligence. And so we can even spin up separate agents that are running continuously in the background. This could be different stuff around research or triaging messages, and this allows you to keep track of different workflows on a day-by-day basis, as well as keep up to date with whatever is going on within your life. Yep. Great. So beyond the interaction over CLI or over the desktop app, there's different ways that we can optimize the experience. And the way we like to decompose this is as a spec. What is the spec composed of? It's composed of all of these different primitives that we discussed before. So the intelligence that you've selected, the agent framework, the actual inference engine, the tools, and the memory. And we simplify this into a single TOML that allows other LMs to optimize over this configuration. So rather than having a user go through and manually change these different configs, we actually have different LMs go through and optimize the config for your actual workflow. And so what this looks like visually is an actual just typed config with all of the different specifications for the LM that you're running, for the agent that you're running, for the tool calls that you're making, all in a descriptive TOML file or JSON. Why do we make it as a single JSON or a single TOML? To make it easier for a user or easier for an LM to optimize over and understand how you're actually running these local agents on device. What's nice about this framework is you can plug and play and mix different primitives as you wish. You can switch out the LM that you're running, switch out the engine that you're running, change the different prompting style and the different agentic structure for actually running your different agents. And rather than having a bunch of different disparate files that are actually being used for running your agent, you have a single configuration that can be optimized in a more direct manner. So to optimize this config, we do something called LLM guided spec search. What does this look like? This looks like a Cloud LM collaborating with a local LM to optimize for your given configuration. So if you have a deep research flow or a deep research agent that you want to optimize over, you allow a Cloud LM to actually diagnose the current ways that that agent is failing, propose new edits to allow you to optimize that config, gate based off of whether those configuration changes improve or whether they cause regressions to your existing workflow. And then, once that final config improves, actually run the whole thing on device. So this allows you to get the best of the Cloud LM by allowing it to optimize and strengthen your existing workflow while running all of the actual day-to-day logic, the day-to-day intelligence on your device. There's a bunch of different ways. There is a bunch of different ways that you can optimize this framework. But what we find is that even with these on-device LM systems, you can rival Cloud LM strategies across the board. This allows you to substantially reduce the dollar cost that you're spending on a day-to-day basis for these different workflows, sometimes even up to 800x reduction in cost. In addition, you can reduce the latency for actually running these different workflows. So rather than having your LM queries scheduled and waiting on it to actually be cleared by some Cloud LM, the LM on your device is running all of your workflows just for you, and you don't need to worry about any sort of external costs or any sort of external delays because of waiting on others' workflows. What we also found is that by pairing these different local LMs with cloud strategies, we were able to strengthen the overall OpenJarvis frameworks across different tasks. And so we wanted to examine whether a local strategy could work for different kinds of coding tasks, for different kinds of personal AI tasks, for different kinds of deep research queries. And what we found that across the board, by pairing these local LMs with these cloud resources, we were actually able to strengthen performance and even rival closed source frontier models with much smaller LMs in the range of 20B to 30B active parameters. Additionally, we find that it's cheaper to optimize these local LMs rather than relying on cloud LMs all the time for the optimization. And so by actually paying this one-time cost of doing this LLM-guided search, we're able to amortize it over all of the different queries that these users were running And this leads to anywhere in the range of 7x to 11x reduction in the dollar cost that people are spending day to day. And that compounds over time as these LMs get better and better, and as the local accelerators get better and better as well. Looking forward, we're really excited to keep expanding the stack, supporting new LMs, supporting new engines, supporting new agentic frameworks. So if any of these things are exciting for you and you're interested in chatting, please reach out to us. We're available on Twitter, GitHub, also our OpenJarvis project page. We're really excited about the personal AI space, and we're particularly excited about how local LMs can collaborate with cloud LMs across the AMD stack. And so we're excited to keep working on this. Thank you so much for your time.